Then here is another filter that's been introduced. It's called crumb, and then there's a variation of it called multi-crumb. So what does it do? Uh, for any two vectors, remember that the server is going to receive n gradients that are vectors of a certain length. For those two vectors, for any pair of such vectors, we can define distance between them, which is simply the norm, the L2 norm of the difference between the two vectors. And having defined the distance, then we're going to compute a score for each of these gradients. So the server has n gradients, it will compute a score for each of them. What's the score? Remember that if you have gradient, let's call it G, let's say G1. Suppose you're computing the score for G1, then we have the other gradients are G2, G3, Gn. So you'll compute the distance between G1 and G2, G1 and G3, G1 and G1, Gn, all of them. Now these distances are just real numbers, right? Non-negative real numbers. Then we find the closest n minus t minus 2 other gradients from there are n minus 1 other gradients. The closest meaning the ones that are the least smallest distances, and compute the sum of n minus t minus 2. So that gives you a score of one of the gradients. We have to compute the score for every one of the n gradients. And then the output of this filter called crumb is the gradient with the smallest score. And intuitively, what we are doing is basically picking the output, the filter gradient as a gradient that is close to most of the good gradients. That's the intuition behind it. But it only picks one gradient. And if you only pick one gradient, that may have high variance. In fact, this particular gradient is, this filter is applied for stochastic gradients, actually. So if the output consists of just one gradient, it may have high variance. To reduce the variance, one can actually use multiple such gradients. So that's the multi-crumb variation where there is a parameter m. So instead of choosing just the one gradient with the smallest gradient, we are going to pick now m gradients with the lowest scores and aggregate or average them and use that as the output of this filter. So here's a simple example of this. Suppose n equal to 5 and t equal to 1, so n minus t minus 2 is equal to 2. And there are 5 gradients where the dimension is 2, so it's in a plane. If this is the origin, then this is the first one gradient, this other gradient. These are all vectors pointing that way, okay? But distance between these two gradients is just the length of this segment. Distance between these two gradients is the length of that segment, and so on. And if I did my math right, then the output of the crumb filter will be the gradient that's shown in red. It's going to find the two closest gradients. For this guy, the two closest gradients are these two, and the score is the sum of, if this is A and B, the score for this gradient is A plus B. On the other hand, the score for, if you take this guy, I think I call this A, suppose this is C, the score for this gradient will be A plus C, and so on. So having computed the gradient with the smallest value, this filter will output that particular gradient. Okay, so like I said earlier, this particular filter was introduced for the case of stochastic gradient, in particular the case where the agents have produced gradients with identical distribution, IID, the IID model. And like I said earlier, even though the gradients have identical behavior on average, the problem is interesting because the gradients themselves are not identical. The stochastic gradients are not identical. Something I have not said yet, which is true for all the filters we will discuss briefly today, is that these papers will have to make some assumptions to show some desirable properties of these filters or desirable properties of the distributed fault tolerant optimization algorithm. In particular, they will generally assume some bound on number of faulty agents or the ratio of faulty agents given a number of agents. So the bound itself may be different for different filters. In addition, there may be assumptions about, in the case of stochastic gradients, there may be assumptions about the variance of the stochastic gradient. or some other assumption about the gradients that may not be exactly the same as bounding the variance, but something similar. And then there may be other, potentially other additional assumptions made about those functions as well. And all that, what it means is that the different filters are not easy to compare because the assumptions they make are often of different form. That makes it difficult to make direct comparisons between them. So when you're looking at different filters, different papers, you have to be careful to fully understand what the problem setting is. Is it stochastic? Is it not stochastic? What are the precise assumptions being made about the cost functions to be able to draw comparative conclusions about these different filters. Here is yet another filter, and I think I'll discuss at least one more. This is a norm-based filter. Remember that the gradients are vectors, and vectors have length of the norm and the direction. And this filter looks at just the norm, ignores the direction altogether. So in brief, the server has n gradients, so there are n norms. What the server does is to take the gradients with the largest t norms, the longest vectors, and make their lengths equal to the t plus 1th vector among the n vectors, the n gradients. That's the whole algorithm. And then you add up all the gradients that server, after this clipping. So suppose that we have n equal to 3 and t equal to 1. Then we are going to take the largest norm, which is the t norms, just one of them. That's the largest norm. We're going to make it equal to the second largest norm, which happens to be 2. So how do you make a vector of length 3? How do you convert the length to length 2? Just multiply the vector by 2/3. And that just scales the vector, keeping the same direction, just changes the norm. And then the filter gradient is simply the summation of these 3 gradients. Now, 2 of them are the gradients that were sent by the agents. This gradient has been clipped, we just add them up, or you can average them, doesn't really matter. Similar behavior. This particular algorithm has been applied to several, in fact, for all the settings in this graph, in this table by now. Here is one more filter that uses geometric gradient median. So suppose that the server has a set of vectors. There are m vectors here. And if you have m vectors, the geometric median is defined like this, where ui here is from this set. So what we're basically doing is for every possible v, we're going to compute the distance of v from each of these ui vectors and add up the distance of vector v from all of these vectors. And then we're going to pick a v that minimizes the distance defined in this manner. We're going to pick a v that minimizes this quantity. And that would be the filter gradient. If you make this set equal to all the n gradients, then that's one version of the algorithm. More generally, what we can do is that instead of using the n gradients as they are, we can divide the n gradients into batches of size n by b. So this is batch number 1, batch number 2, batch number b. And then compute the mean gradient for each batch. So now you end up with n by b gradients, where each of those n by b gradients is a mean or average of gradients within each batch. And then we take geometric median of that. This has been applied for the setting of stochastic gradients, where again the agents have IID. Agents produce stochastic gradients from an IID distribution. And there are many more filters by now. Here is a pointer for one of them that uses a robust mean estimation method that was proposed previously, but applies it for the context of distributed fault tolerance. So before I wrap up discussion of fault tolerance, I want to add some caveats. One is that the discussion here is not meant to be comprehensive. There are more gradient filters, more algorithms that have been proposed. And there are some omissions that I think are notable that you may want to look up later on. In particular, this second paper here, that's called Learning from History, considers the idea that perhaps instead of the server using just the current gradients that are received from the agents to take the next step to compute the next estimate. Perhaps the server should keep some history of the gradients that it has received previously from the agents. For example, it may keep a weighted average, exponentially moving average of the gradients received from the various agents. That's just one possibility. And the question it is asking is whether having this history available somehow helps in improving the behavior of fault-tolerant optimizations. And the conclusion from the paper is that perhaps it does help. This is relatively new work. There is potential for doing more research along that direction. This paper, which is in fact from my group, observes that many of the papers on distributed fault-tolerant optimizations are using proactive redundancy, meaning that we are using a lot of agents upfront, let's say for exact resilience, so that if anything bad happens, if there are bad agents, then we can just filter the behavior of the bad agents and get a reasonable output from the algorithm. An alternative is to not actually tolerate bad agents, but just detect the existence of bad agents, and maybe not even detect completely accurately. Maybe there is some false positive and false negative in the detection algorithm. But what if we can detect the presence of faulty agents? And if we could do that, then maybe we can bring extra redundancy into the execution only when we think there are bad agents in the system. Because in most systems, most likely there is no bad behavior at all, or the number of fault agents may be quite small, even though we maybe wanted to tolerate a larger number of bad agents. And this reactive redundancy idea basically says that somehow some combination of detection mechanisms and the ability to deploy extra redundancy dynamically can improve the overhead of achieving fault tolerance. And there are variations on the theme that one can develop. And in fact, I have a master student who is finishing up his thesis that builds on the ideas from this paper. The thesis should be available later this summer of 2021. One last caveat, I discussed several filters, and they all achieve reasonable output, a reasonable outcome. So what I did not point out specifically is that the norm-based filter that I introduced, we have shown that it can achieve exact resilience, approximate resilience, both that I introduced earlier, but with some assumptions on those cost functions, right? Some assumptions about how many falls we are going to tolerate, and so on. It's a very simple filter. It just uses the norm of the gradients. It ignores the direction, which one would think is quite critical actually for correctness of algorithms. But the reason it can do that is because it's making some additional assumptions about the cost functions, additional assumptions about how many faults you have. And in fact, the fraction of faulty agents depends on the property of the cost functions themselves, such as the Lipschitz constants and storm convexity and so on. So in general, as you might expect, if the filter is simpler, for correctness, you're going to have to make more assumptions, more stringent assumptions about the cost functions. Whereas a function that is more complex may be able to get away with by making fewer assumptions about the cost functions. And like I said earlier, this particular issue makes it very difficult to compare different filters. So be very careful when you look at different papers before one decides whether one filter is better than the other. One has to look at the various assumptions people are making. So with that, we are going to wrap up the discussion of fault tolerance and go and discuss privacy next. Okay, so let's consider privacy-preserving optimization and learning algorithms. We'll take a few examples of those as well, similar to the secure fault-tolerant algorithms that we discussed earlier. And here we'll consider algorithms for the server architecture as well as the decentralized or peer-to-peer architecture. Just to remind you then, the server architecture that we saw previously, we have a server that maintains an estimate of the minimum of sigma FIX, and that estimate gets updated iteratively. In each iteration, the server sends the current estimate to the agents. Agents send back to the server their gradients, and then the server computes a new estimate. In the privacy literature, we are going to assume that all the agents and servers perform the computation correctly. Nobody's tampering with information, but the goal is to preserve privacy if possible. Now, if you consider the case of server-based architecture, then in the algorithm we just saw, the agent supplies a gradient to the server. And as you can imagine, the more gradients the agent supplies to the server, the more it's going to reveal about itself, its own cost function to the server. For example, if the cost function happens to be a quadratic in x, suppose x is a scalar and the cost function is a quadratic, then the gradient function is just a linear function in x. And all you need now are two values of the gradient at two distinct values of x to learn the gradient function completely. And so in general, of course, the functions will be higher dimension, but the more communication that occurs between the agent and the server is likely to be able to learn more about the cost function of the agent. And then the question is, can you achieve privacy, some measure of privacy for the cost function of the agents, and yet collaborate with each other and the server, in fact, to optimize this global cost function. Turns out that there are ways of improving on the privacy compared to the baseline scheme. And something similar would happen in the iterative algorithms as well. We saw the algorithm previously. In fact, we took this example. And in this example, the agents talk to to their neighbors in each iteration and obtain the current estimates of their own neighbors. And then in yellow, we have this weighted averaging, which is also sometimes called the consensus step. Here, the weighted averaging is over the estimate of the agent itself and the estimates provided by its neighbors. And then there is a gradient descent step that we saw previously too, where the gradient used in the gradient descent step is that of the cost function of that individual agent. So if this equation shows the update happening at agent 1, and therefore it's using the gradient of its own cost function f1. And similarly, agents 2 and 3 perform the weighted averaging or consensus step on the estimates, and then the gradient descent step to get the new estimate of the minimum at that agent. And similar to server-based architecture, in case of peer-to-peer or decentralized architecture as well, the more the nodes communicate with the other neighbors, other nodes, they can potentially reveal something about their cost function. And again, we would want to have some notion of privacy. So question is, how do we go about doing this? So distributed optimization is just one example of multi-party computation. There is a large body of work on cryptographic techniques for multi-party computation. And one can apply some of those in principle to optimization as well. But there are other methods such as differential privacy and what I'm calling function transformation here, but later on we'll see that. I'll get into some details of that. But the cryptographic method, and this slide is not meant to be describing any particular scheme. I'm not going to discuss cryptographic techniques much at all, actually, in this tutorial. One may try to use cryptographic techniques for distributed optimization. However, they tend to be more expensive than the two algorithms, two techniques that we're going to discuss next. And so I think we have to do more work to obtain efficient cryptographic techniques for achieving privacy for distributed optimization. As far as I know, such efficient mechanisms don't exist yet. For example, one might want to use homomorphic encryption or something like that for distributed optimization, but then those encryption schemes have to be cheap, computationally cheap. The other two approaches, I mentioned differential privacy as one of the approaches that may be usable. And so there is a fair amount of work on differential privacy for machine learning or distributed machine learning, deep learning, and distributed optimization in general. So in the distributed architecture that we are considering, the algorithm that we discussed previously, there is a server that maintains the estimate of the minimum. And normally, those agents will send their own gradient, the gradient of their own cost function, to the server in each iteration. For example, agent 1 will send gradient of function f1 at xk in the kth iteration. Or if it is stochastic gradient descent, then it will send a stochastic gradient for function f1 at xk in that iteration. But the stochastic gradient is such that the expected value of the gradient will be 0. So it's an unbiased estimate of the gradient. So to achieve privacy, algorithms have been proposed to modify this server-based optimization algorithm by adding some noise to the gradients that are being supplied to the server. And the purpose basically is to, in effect, hide the cost function of agent 1 or agent 2, agent 3 from the server. And the only way to hide the cost function is to essentially provide information that does not represent the cost function exactly. So if I supply the gradients exactly to the server, of course, I'm not hiding anything. And so if I want to hide something compared to what the baseline algorithm provides to the server, then I must somehow make the communication noisy. And the differential privacy schemes often use this noise that is Laplace distributed. And so in this example, what agent 1 is doing in iteration k is supplying the gradient to the server, but it's been modified by adding some noise, deliberately adding some noise to the gradient. Epsilon, the noise here is epsilon k, which is produced using Laplace distribution, which makes it easier to analyze the differential privacy of the scheme. And so this particular method was introduced by Chokri and Shvatikov in 2015 for the server-based distributed deep learning algorithms. And they have, this is not their entire scheme. They have a few other details to their scheme, but as far as the privacy aspect goes, this is one of the key elements of their algorithm. And in the context of deep learning, these gradients come from the data that the agent might have. This is a gradient of the loss function. And then the question is, what are we trying to hide? What are we trying to achieve privacy of? Is the privacy of the data that is available to that particular agent. So the goal of these differential privacy schemes, in the case of deep learning, would be to make it difficult to determine if a particular data item was used during the training of a neural network, for example. So the server is receiving these gradients that are modified with noise, and server may want to know what data is being used to generate these gradients or to generate the network parameters by way of performing distributed optimization. And the goal of privacy is to avoid, sort of prevent that server from learning that. And I'm not going to go into the details of the analysis, but these papers will usually have either a theoretical analysis of these schemes or some kind of empirical measurement, evaluation of the proposed privacy schemes. But at a high level, this differential privacy algorithm is quite straightforward. All we are doing is adding noise to the gradient. But what that also means then is that the server is not actually receiving gradients of the true cost function. And therefore, the gradients correspond to a cost function that is not the true cost function. And obviously, if the gradients are being used are not accurate, then we are probably not going to optimize sigma fi anymore. The outcome of the computation will be some estimate x that is not exactly equal to the argmin of sigma fi x. But that's the price of privacy here. So we lose some accuracy in return for privacy. And there's a trade-off. The more privacy we want, meaning the more we try to hide from the server, the less accurate the estimate might be. And so one has to decide how much accuracy you want to trade off for privacy. Here, by accuracy, I mean that the estimate x may not be equal to the true argmin, or may not even be close to it, depending on how much privacy you're trying to get. But of course, in the context of machine learning, there is also this other notion of accuracy that says how well does a resulting machine, if it is a classifier, how accurately does it classify? And it turns out there is a trade-off between accuracy and privacy as well, as you might imagine. Now, similar algorithms have been developed for decentralized or peer-to-peer optimization as well. And we saw this slide previously, but I want to repeat this just for a minute because we'll come back to it when we discuss algorithms. But the basic idea was that each agent is maintaining its own estimate of the minimum, And then in each iteration, they exchange the estimates with their own neighbors. And the neighbors, as we saw, perform the weighted average and then take the gradient step. And we saw this previously as well. So if you want to achieve differential privacy, then you want to modify this algorithm somehow. And as before, what the agents will do is to modify the information they're sending to their neighbors so that the neighbors will learn less than they would have learned using the baseline algorithm about the cost function of the sender agent. So the idea is the same or very similar. Agents add noise to their estimates before sharing their estimates with the neighbors. Now, there are actually several papers on this particular problem, meaning achieving differential privacy for the peer-to-peer architecture. At certain level, the algorithms look similar, but often their analysis may not be identical, meaning they may be analyzing slightly different notions of privacy here. So one notion of differential privacy for peer-to-peer architecture is that, remember that we are trying to minimize the sum of n cost functions, F1, F2, F3, and so on. And one might want to hide whether one of those n cost functions is equal to F, star, for instance. Right? I may have a particular cost function in mind, and I might want to know whether one of these agents has that cost function or not, which is analogous to knowing whether, what data set that agent may have if this is a neural network training kind of optimization problem. But in an abstract sense, what we're trying to hide is just the cost function of the individual agents. And there are other variations on the notions of differential privacy that the different papers analyze. And I have cited this paper here, which is in fact with my colleagues at Illinois several years ago. And then there is a fair amount of other work as well on differential privacy for optimization and learning. I've cited a couple of papers here. I think I've said this before, but if you, I will post the slides for the tutorial on my website, for which I gave you the link earlier, and I'll give a link later at the end of the talk tutorial as well. And when you click on these links, these names here, they will take you to the papers that I'm citing. So I don't have a separate reference list per se, but you can just click on these links. Now, we looked at one server-based architecture where each of the agents maintain an estimate, rather each of the agents knew their own cost function. The server maintained the estimate, and the server would send the estimate to the agents, and then the agents would upload the gradients to the server. Now, in this so-called federated architecture, the behavior of the agents is slightly different. The server maintains an estimate as before, but then the server sends the estimate again as before to the different agents. But what the agents perform is actually a gradient step. So for example, if you look at agent 1, it will receive the estimate xk from the server, and then it performs a gradient step using its own gradient locally. So what agent 1 will do is to compute xk minus yk times the gradient of cost function f1 at xk. And this will result in computation of y1 at agent 1. Similarly, agent 2 will compute y2, agent 2 will compute y3, and they will send this back to the server. And at the server, the xk, the new xk, or the xk plus 1, will be computed simply as an average of these y values received from the different agents. If you think about it for a minute, this algorithm, the way I described, is actually no different in its effect as from the previous algorithm, where the agents applied the gradients and then the server averaged the gradients and took a step in that direction of the average gradient. These two are completely equivalent, except that now we can modify the federated architecture a little bit to take multiple steps at each agent before sending the y value to the server. So here is the modification. So at each agent I, instead of performing this step once, right? What you notice here is that I received the value of x, took a step in the direction of the gradients once, and computed the new value of y. Instead of that, we can now replace it by multiple steps, meaning that I receive xk from the agent, compute the gradient at that value of xk, subtract from the current estimate, right, to get a new estimate. Now I'm at the new estimate, I'll take the gradient at that estimate, subtract that. I have yet another new estimate, and so on. I can take multiple steps like that and then upload the resulting value of y back to the server. Now, if you do it this way, then of course the two algorithms are not equivalent anymore. And, and in fact, just taking multiple steps like that, uh, perhaps the gradients we use don't have to be the full gradients or exact gradients. They could be stochastic gradients. And the stochastic gradients are random, right? Because these are drawn from some distribution, and the randomness is not known to the server in general, right? The agent decides how to randomly choose the stochastic gradient in a particular step. The randomness itself gives the agent some extent privacy, but what we are going to do is to actually add one more layer of privacy on top of that. So anyhow, this is the so-called federated architecture. It's similar to the architecture we saw earlier, but not quite the same because of the agents are doing, the agent's behavior is actually quite different compared to the previous algorithm. So there is work on providing privacy for the federated learning architecture as well. And this slide, it's a bit busy, the slide, but the ideas are simple. So I'll go slowly over the text in this slide. But the basic goal for that, what I'm describing on the next slide, is to perform this averaging at the bottom of this slide here, this sigma I divided by n, just the averaging step to compute the xk plus n. So we are just focusing on the averaging here. What the agents do doesn't change. So how do you do the averaging without revealing your own value of y to the server is the question. That's the goal here. So the server wants to compute the summation of y or the average of y, but the agents don't want to reveal the value of y to the server. And so here is a technique, and we will see a similar technique being used later in the talk as well for other schemes. So in the basic idea is that each pair of users or agents communicates with each other over a secure channel so that others cannot hear what they're sending to each other. And so let's consider two agents or two users, U and V. And user U generates a value, some noise value. Let's call it S U subscript U comma V to user V. So it picks a random number, user picks a random number and sends it to V. And similarly, V will send a random number to U. In fact, each user is sending a random number such as this to every other agent of the system. And having received these random numbers from the other people, other users, other agents, user U now takes the value of y that he has on the previous, here is the value of y that he is computing, and he hides it by doing this computation. So what does this computation do? It says y equal to sigma, y equal to sigma of these random values that user U has received, right? Those values I'm adding, minus the random values that user U has sent to other people, right? So you start with the value y, add the values received, subtract the values sent, and all of this is happening under a modulo operation, modulo r, where r happens to be a number that is large enough to ensure correctness of this privacy-preserving aggregation operation. And you can, in fact, work out how large R needs to be quite easily if you think about it for a few minutes. Now, what the server is going to do basically is that he's going to receive all these y values, or rather the z values. These are modified y values. Now, just looking at z value now, the server cannot really tell what the y value is. This modulo operation actually hides the y value quite well because these random values are not known to the server. The server cannot infer the value of y knowing the value of z. However, it can compute sigma y from sigma z by just adding up all the z's and doing the modulo operation, again using the same r. And this technique allows the server to compute sigma y and at the same time provides privacy to all the agents. Of course, it's expensive because these agents have to talk to each other to generate these random values and so on. But this is just the basic scheme that was proposed by a group out of Google, I believe, in 2016. And there are a few more optimizations to the basic algorithm to make it more general and make it somewhat more efficient. And this is just one example of a privacy preserving scheme for federated learning. Since then, there is more work along similar lines that you might want to look at. In fact, this idea of exchanging random numbers to compute the sum securely or in a privacy preserving manner has been introduced in other work as well. And I'm giving you a link to one such paper here. And in fact, we have used similar ideas in our work, and there are other people who have been exploiting this technique as well in their work. Okay, so what we have done so far, I did not really discuss cryptographic technique, but those have been introduced. Not very many, but there is some work using cryptographic technique. We discussed differential privacy for the server-based architecture, including this, and as well as a peer-to-peer scheme. And then we discussed this secure aggregation idea, which also provides privacy. In fact, we could use the same secure aggregation idea for the first server-based scheme as well, where the secure aggregation will be performed on gradients instead of the estimates. And the same technique should work there as well. And I want to introduce one more idea. I think this is the last idea I'm going to introduce, but a couple of variations on that theme, where unlike the previous scheme where the agents were introducing noise for the purpose of differential privacy, and the noise was introduced for the purpose of providing privacy, but the noise also resulted in incorrect or essentially it did not produce the same argument that you would have produced in the absence of noise. So noise was good for the purpose of improving privacy, but noise would be bad in these algorithms because it may degrade the accuracy of the computation that we are performing. And so now the next variation on the idea is to actually introduce noise that is cancelable in some sense, so that even though the servers are receiving noisy values of gradients, for example, the resulting computation will still have some accuracy, or actually accuracy comparable to the noise-free baseline algorithms. And as we will see very soon, this notion of cancelable noise has some similarity to the ideas that we just saw on the previous 2-3 slides. However, there are differences in the manner in which the noise is used, and therefore it results in different outcomes. So here is the idea of cancelable noise applied to a server-based architecture. To apply this notion of cancelable noise or balanced noise, as the slide says here, to the server-based architecture, we are going to need multiple servers. This idea doesn't work with just one server. And so that's the price being paid for accuracy. It needs multiple servers. And the scheme provides privacy if and only if a subset of the servers is adversarial, meaning in this example, for instance, we have 2 servers, and if only one of them is trying to learn my data for the sake of diverging my sort of so only one of the servers is adversarial, wanting to learn my data. The other one is not trying to do that. So if only one server is adversarial, the other one is not cooperating with this server to compromise privacy, then this scheme will provide some notion of privacy. So let's get into the details of that. But at the key principle is to introduce noise in some structured way. It's not completely random, so that it cancels over all the servers. Or when we apply this to peer-to-peer schemes, the noise will cancel over the network somehow. So we haven't discussed distributed optimization with multiple servers yet, but the algorithms for multiple servers are actually quite similar to single server in the following sense. Each server will maintain an estimate of the minimum of sigma fi, as we saw before. We had one server then, but now we have 2. Each of them maintains its own estimate. Each server talks to the agents, either all the agents or some of the agents in the system. And in each iteration, each server will send its own estimate to the agents that it communicates with. And then agents will compute gradients of their own cost function at the estimates they receive from the server and send back those gradients to the servers. So far, This is looking very much like what we did for single server, except that now there are multiple servers doing the same thing. But then now there is an additional step. Every once in a while, the servers will talk to each other. Remember that each server is maintaining its own estimate of the minimum of sigma fi, but these servers will want to reconcile their estimates every once in a while, maybe every iteration, maybe after multiple iterations. Or the reconciling is essentially where you exchange the estimates with each other. And in the case of two servers, they'll simply take the average of those two estimates. In general, there may be multiple servers, there will be more than two servers. They may be connected to each other in a complete graph, meaning everybody is talking to everybody, or they may be connected in some incomplete graph. But either way, you can design this server protocol, meaning the protocol for reconciling estimates among the servers such that the final computation results in computation of the final result will be computation of the argmin of sigma fi at all the servers. And so this is a multi-server architecture. We don't need to worry to know right now too much detail about it, but I think I've given you the key ideas behind it. So how do you utilize this so-called cancelable or balanced noise? So in this example, I'm assuming that there are two servers, three agents, and in fact, both the servers talk to all the agents. But you can generalize this idea where not every agent talks to every server, and in fact, with more than two servers. So the intuition is that each server is going to, remember each agent, each agent, remember that each agent has a cost function. Agent one has cost function F1, agent two has cost function F2, and so on. But now we are going to have each client or each agent simulate multiple clients or multiple agents. So in this example, each agent is actually going to simulate two agents. Actually, I'm calling them clients in these slides. So I use agents, clients, nodes, users. These are all jargon for the same thing. So in this example, each client is simulating two clients in a particular way. So client one had cost function F1 is going to simulate two different clients, right? The first of these new clients will have cost function F11, which is shown here. And the second of these simulated clients or agents will have cost function F12 of X. These functions are chosen such that F11 plus F12 equal to the actual cost function of agent one. Similarly, agent two will simulate two agents, one with cost function F21, the other with cost function F22, such that F21 plus F22 is equal to F2, and so on. Now, even if the original cost function F1, F2, F3 may have been convex, these component functions, F11, F12, that I'm splitting F1 into, so you can think of F1 being split into multiple functions, in this case, two functions. This individual F11, F12 do not have to be convex. So it may be the case that the sigma fi is convex to begin with. And if we satisfy these kinds of constraints, then summation of these new cost functions, F11, F12, F21, F22, F3, F31, F32, summation of these six cost functions will still be equal to sigma fi that we started with, and it will remain convex. But now we have a situation where we have six cost functions that may not be individually convex, and yet their sum is convex. So we have a convex sum of potentially non-convex cost functions. There are six of them. Now, in this new picture, what you see is that there are three agents talking to server one. There are three agents talking to server two. And so this algorithm, there are algorithms known for distributed optimization. In fact, I explained one to you earlier, where each server talks to certain agents and performs the gradient steps that we have seen before for the single server architecture. And then every once in a while, the servers interact with each other to perform this averaging or consensus step. These algorithms are known to converge to the minimum of the summation of all the cost functions for the case when the individual cost functions are convex. But it turns out, as we have shown in our work, that as long as the summation of the cost functions, in this case, six of them, is convex, even if the individual cost function is not convex, the algorithm will still converge to the minimum, the argmin of the summation of these six cost functions, which is in fact equal to the summation of fi that we started with. So in effect, this algorithm will obtain argmin of sigma fix, even though we are simulating more clients than we had to begin with. So what does simulating these clients buys us is that, actually I said everything on this slide earlier already, so I won't repeat it. So what does it get us is that we can solve the problem we set out to solve. There are some assumptions being made. For example, there are assumptions about the gradients being Lipschitz and so on. These are technical assumptions that one needs to be able to prove the properties we want to prove. But what does it give us as far as privacy is concerned? So think about server one in this picture. Server one is talking to these simulated agents now. One of these agents has cost function f11. One of the agents has cost function f12, and one of the agents has cost function I'm sorry, one agent has cost function f11, the other has f21, and the third cost function is f31, right? So the first of the simulated agents at agent one, the first of the simulated agents at agent two, and so on. So in the worst case, server one may learn f11, or more accurately, if you're exchanging gradients, it will learn the gradient function for f11. That's the most that the server one might learn. So let's just grant that server one learns f11. That's you can't learn more than that, because server one is only talking to this simulated, the first simulated agent that has cost function f11. It may learn f21 similarly and f31. So the most that a server one can learn are these three component functions, f11, f21, and f31. Now, what server one and server two exchange with each other are results of the aggregation step, right? Meaning server one updates its own estimate using the gradients received from these three simulated agents. And then during the consensus step is going to exchange this new estimate with the other server. In effect, the most that server one might reveal to server two is the cost function, the summation of f11, f21, and f31. So in other words, and similarly, server two, the most it might reveal to server one is summation of f21, f22, and f32. And so this is what I'm trying to say at the bottom of the slide. Server one may learn, the most it might learn are these individual functions f11, f21, f31, and summation of the other three functions that are being simulated. However, it is not going to learn directly f1, f2, or f3. And in fact, if you choose these split functions well, then the f11 will reveal very little about f1, if anything. And similarly, f2 will reveal very little about f2. And so this is the notion of privacy that we get from this architecture, that even though the end result of the computation is correct value for the argmin of sigma fix, the servers are not able to learn the individual FIs accurately. And how well we can hide them depends on how we choose F11 and F21. So in some sense, if we make F11 and F21 very noisy, right, we're going to add, F11 will be F1 plus some noise, which is really F21. If they're more noisy, then of course we'll hide F1 better. But making these more noisy might increase the convergence time for the algorithm. Even though you'll obtain the correct value of the estimate in the end, it might take longer to get there because we have made these functions more noisy. If you think in terms of Lipschitz constants, maybe this F11, F21 may have a large Lipschitz constant because we're making them noisier. But the key is that we can achieve the correct outcome at the end of the day. The other observation you should make is that if you know, knowing what server one knows, if you add up everything it knows, all the F11, F21, F31, and the red sum, that corresponds to sigma fi. So if you grant all this to server one, then server one actually will also be able to compute the summation of cost function fix actually during this algorithm. This is a very conservative analysis, but even though it can learn the summation of all the cost functions, it's not going to learn the individual cost functions. So this idea of taking f1 and dividing into two functions is what I'm calling function splitting here. It is not necessarily practical, because if you think of f1 as a loss function over a lot of data, it's not exactly clear that you want to actually enumerate the whole function and then split it in this manner. But this was intended to provide intuition behind the algorithm. For functions that are compact and described in a compact way, this may be a usable technique actually in some other context, maybe in linear regression or something like that. But the other way to do it is to use structured randomization. By that I mean that, as we saw previously for differential privacy, one way to provide privacy is just add noise before uploading the gradient. Well, we could do the same thing here. So let's just focus on function the agent number one. Remember, in my intuitive explanation, it was simulating two agents. It won't do that anymore. But what's going to happen is that it's going to supply gradients to the two servers. And what it is going to do is to add some noise to the gradients it's going to supply to the server. And the noise can be additive or multiplicative. And in my illustration, I'm going to illustrate multiplicative noise. So normally what should happen is that the server one should upload to agent one. Agent one should upload to server one gradient of cost function f1 at that estimate maintained by server one. Let's call it x superscript one here. That's what it should upload to server one. And similarly, it should upload to server two the gradient of cost function f1 at the estimate provided by server two. But instead, what it is going to do here is to scale those gradients by some factor and upload them such that the factor adds up to a one. And the additive noise is similar, where the agent one will add some noise, let's say epsilon one, to the gradient sent to server one, and add noise negative epsilon one to the gradient sent to server two. So if you look at what each server is receiving from the agent, the gradient is actually noisy. And in fact, that noise may have non-zero mean. It doesn't have to have a zero mean. It will be noise with non-zero mean, possibly. But if you take the noise added to the server one and combine that with noise added to server two, actually it cancels out, right? Because I'm adding epsilon one to server one and minus epsilon one to server two. When you add, they just cancel out. In the same iteration, in fact, the algorithm works correctly even if the noise doesn't add to zero immediately, meaning we can look at the noise added by agent one to server one and server two over this iteration to the next 10 iterations. And we can design the noise so that all of that, when you add together, it adds to zero, even if it may not add to zero in a given iteration. So it will add to zero over a window of time, and not necessarily in a single iteration. And even then, the algorithm will result in the correct calculation of argument sigma fi. As before, we won't actually do proofs here. But the key is that we are adding noise that somehow cancels out over, in this case, the communication to different servers from a given agent is noisy, but over time, it cancels out. And if you make some technical assumptions, then you can show that these kinds of schemes actually do produce the correct outcome. One can apply the same idea or a similar idea to peer-to-peer architectures. And there are several papers, actually, some from my group and some from other groups, that have proposed schemes like this over the last several years now. So we saw that in the example of the peer-to-peer or decentralized optimization, that each agent sends to his neighbors his current estimate. And what we're going to do now is to add some noise to that estimate before sending to the neighbors. And we will pick the noise so that the noise cancels out over time and space. By time, I mean the noise. Maybe you have to look at the noise added over a sequence, a duration of time. And by space, I mean the noise I add in my communication to my different neighbors. If you look at the space and time over some finite horizon, we will guarantee that it adds to zero. And that suffices for correct outcome of the computation. Okay, so let's look at one of these schemes where the noise will cancel over the neighbors, or we can have other schemes as well, that for which I have slides, but maybe I won't talk about it too much. So here is a simple illustration. You have agent F3, as we've seen before, in a given iteration of the algorithm, F3 should be sending his current estimate, which I'm calling simply X in this slide, to his neighbors, which are agents 1 and 2 in this example. But instead, what it does is to send the estimate with some noise, epsilon 1 to agent 1, and adds epsilon 2 noise to the estimate sent to agent 2, in this case, such that the epsilon 1 plus epsilon 2 is equal to 0 in the current iteration, or like I said, if you take the noise added to these two estimates over, let's say, this iteration, the next, and the next 3 iterations together, then all the noise values together, 3 iterations will cancel to 0. If there are 3 neighbors of node agent 3, then you add noise epsilon 1, 2, 3 to the 3 neighbors, and that will add to 0 over some finite duration of time. And that's what I mean here by adding balanced noise or cancelable noise that cancel over just my neighbors. And that this will be true for every agent. Each agent will add noise to the estimate sent to its neighbors so that no individual neighbor will receive the actual estimate from the agent. Now, clearly, if all my neighbors cooperate with each other to compromise my privacy, this wouldn't improve privacy at all because they can cancel all the noise, right? If all my neighbors talk to each other, then they can get rid of this noise by just adding what I'm sending to them. And so this scheme doesn't give you privacy if all my neighbors are compromised, but if all my neighbors are not compromised, then you can actually get some privacy. And there are other variations on the idea as well. In fact, what I explained here is sort of written here a little bit more mathematically. So we won't dwell on it too much. So here, the first 2 steps are adding noise and sending the noisy values to the neighbors. And then, like we saw in the decentralized algorithms, each node will receive these estimates from the neighbors. They have their own estimate. It will do weighted averaging of that and then do a gradient descent step where it uses its own gradient. So that part doesn't change. The only thing that is changing is what each agent sends to his neighbors. Other than that, the algorithm is the same. We saw this previously. The network balance noise is quite similar to what we just discussed, with the difference being how the noise is computed. And in fact, how the noise is being computed is similar to the schemes that we saw earlier for secure aggregation, where each agent talks to his own neighbors and figures out what the noise should be, with the distinction being that in the previous discussion of secure aggregation, we had a modulo operation, modulo R. That doesn't happen here because of the way these noisy values are being used. Modulo operation will actually destroy the correctness of the algorithm, and therefore there is no modulo operation here. So again, this scheme is very much like the one I just discussed, except that the noise is computed somewhat differently. There is yet another view of what's happening here that is similar to the function splitting scheme. So let me talk about that for a minute, and then we'll conclude the presentation today. So remember that each agent has some cost function f1. Actually, I'm not doing any analysis here, but for the analysis that we do for this particular scheme, we assume that the function is a bounded degree polynomial of some known degree, known upper bound of the degree. And similar to the function splitting scheme, the view here is that each agent is going to pick a new cost function. In the function splitting scheme, each agent simulated 2 agents with cost functions f11, f12 for agent 1, for example. These are the new cost functions. Here, each agent I has a cost function fi, and is going to instead choose a new cost function f hat of I, such that sigma fi is equal to sigma fi hat, so that the summation of the cost functions remains the same, but these new functions with the hat on them are noisy. They're not the same as the original cost functions, yet they preserve the sum of the cost functions. So how do you pick the noisy function? This is kind of like the secure aggregation scheme, except that now we are doing that trick of talking to the neighbors to pick random numbers. Instead of picking random numbers, we're picking random cost functions. So here is what's happening. Each agent J sends to his neighbor some cost function, some function rather. Let's call it Sji, is going from J to I. And similarly, I is sending function Sij to J. And node J can pick this Sij in whatever manner it wants. Having done that, node J will compute this value, or this function actually, where it is adding up the functions received from the neighbors and subtracting the functions it sent to the neighbors, right? So this is the sum of functions received from neighbors, received by J, minus the functions that J sent to the other neighbors, to his neighbors, and then the f hat is obtained as the f function plus this noise, the noise function. so that together now we have a new system where each agent has cost function f, each agent j has cost function fj hat, and now they can use the distributed or the decentralized algorithm we saw earlier on these new cost functions, and it will result in minimum of sigma fj hat, which happens to be equal to sigma fj. And therefore, we are solving the problem that we set out to solve to begin with. Again, like before, even if each individual fj might have been convex, fj hat may not necessarily be a convex function, and yet the algorithm was correctly under some technical assumptions about the cost function. The privacy here, this is what I was alluding to earlier. If all my neighbors are compromised, of course, I get no privacy at all. But what you can show is that if the graph, the network that the agents are connected by, has connectivity f+1, I think we called this the number of bad agents T earlier. Here I'm calling it F. But if the connectivity is greater than the number of agents trying to compromise privacy, then you get a notion of privacy, meaning that these bad agents that are trying to learn my cost function will not be able to learn my cost function if you have enough connectivity in the network. Or this here should have been, yeah, so this sigma fi hat is equal to sigma fi, which is what I'm calling f of x on this slide. Okay, so that's really all I'm going to be able to present today in this tutorial. So what we did initially was to talk about fault tolerance or secure optimization. We discussed some simple examples of this of fault tolerance schemes that have been proposed. In fact, we discussed several filters that have been proposed that differentiate these different schemes for fault tolerance. And then we looked at a couple of 3 different approaches for privacy in this setting. And as I said before, this presentation is not comprehensive by any means. And in fact, more work is needed in both privacy as well as security of distributed optimization and learning. Plenty of open questions. The open questions really in both cases have to do with improving performance of these algorithms as well as maintaining accuracy. I think I said this previously. I have a longer version of this tutorial that's available from my website, which is linked here. And I'll make available the slides for this tutorial as well on the same website. So you'll access to the slides and the links to the various references. Thank you.